question this year for me. So we are halfway through the year 2025, and it's already shaping up to be an exciting one for innovation. And we are happy to bring you the most cutting edge trends and breakthroughs. So whether you are a seasoned engineer, whether you're a tech enthusiast, or just someone curious, to know what's next, we ask you to please tune in, and we've got you covered. So in today's edition of Camry Technology and AI, we're just powered by Ride.ai. By the way, if you are joining us on our YouTube channel, we kindly ask you to subscribe, and also you can follow us on Instagram to keep updated with a lot of these technology trends that we try to bring to you. We had our maiden webinar 2 months ago, which was presented by Dr. Engineer Giles Tete in AI in healthcare, which went quite well. I think a lot of us were excited about it. Just in case you missed out on that, kindly check that out as well on our YouTube channel. Today, we are diving into a different topic, but in the same AI ML domain. So today we are going to know a bit more about Johnny and in AI in robotics. And this will be presented by none other than Ben Duffy. So Ben and I think we've known each other for some time now. And Ben is an amazing engineer. He's done so many amazing things in the tech space, embedded AI, ML, in healthcare generally. I think he'll do more justice talking about this than me here. Just a little bit of house rules. Everyone is going to be on mute while Ben takes us through his presentation. And if you have questions, kindly drop them in the chat. I think halfway through the presentation, we'll pause for Ben to address some questions if there are any. And most of the questions will be addressed towards the end of the Q&A session. So I think that will be all from my side. And without spending too much time, leave the floor for Ben to tell us about humanoids in AI and robotics. Thank you.
Can you hear me?
Yes, Ben, we can hear you. We can hear you.
Hi, so I'm Ben Duffy, and this is Johnny you see here in these GIFs. He's my little gremlin. And we have many different topics to talk about today, but they're all related to robotics in some form. So I will introduce myself, my YouTube channel, and a lot of details about Johnny's hardware and software. And then I will focus on a specific application, Johnny's trials and tribulations and our joint struggles with suck picking. Maybe a lot of you aren't that familiar with robotics, so I can explain more if needed. And a lot of fields have to come together to make robotics work. For example, computer vision and control. But AI, that is deep learning, is even beginning to eat this field, which is similar to what happened to the fields of computer vision in 2012 and natural language processing from 2016 onwards. That is, LLMs are also coming for robotics too. Then I'll talk about the present and future of robotics, that is imitation and reinforcement learning, and foundation models for action. Things are changing quite fast. And in fact, just to give you a sneak peek and to motivate you to stick around till the end, I'll show you my last slide. I'll begin at the end. And don't worry, we'll cover these topics at the very end. There's a lot of different things here. So I mentioned already imitation learning and reinforcement learning and these foundation models for action. And warning, as you can see, there's a lot of juicy GIFs in these slides, like these ones. I do have a problem with GIFs. But before we get to the end, and to Johnny, of course, I'll say a little about who I am and how I got here. So I've had a kind of crazy 11-year journey through technology, beginning in hobby game development and full stack web dev. And then I got obsessed with AI in 2015, which of course led to ML, DL, ORL, all of these different fields. I did my undergraduate thesis in computer vision in 2016 and worked as a data scientist for 2 years in Accenture. So generally, I love to index, keep up to date, and survey different fields in and related to AI. And as part of a non-profit I founded called MTank with two others, we wrote many different white papers, these survey papers, on progress in AI. For example, in the top left here, we wrote a year in computer vision about the progress that happened in just 1 year in the field of computer vision. In 2018, we released multimodal methods, which was about combining vision and language. This is the power of deep learning. It just has to take tokens or data from many different formats, for example, vision, language, and is able to combine them. And then we even created a reinforcement learning course in 2019. This interest in RL, which is about agents who perform actions to maximize reward, is quite related to robotics, which is generally about machines that can control motors to do work in the real world. Some form of AI is needed to bring this intelligence to an embodiment, that is, a body. I mention all these technologies because they're all useful to some extent for robotics. Even game development is a little like the simulations I will talk about later. So in 2020, the three of us in the nonprofit, we moved to Berlin to form a startup called Bearcover. And on the left here, you can see us experimenting with this monstrosity. It's not my first rodeo in sock picking. This is called mobile manipulation. So it's a differential drive base, like a Roomba robot on the bottom. And there's a large arm for picking up objects for manipulation, for example, socks, putting the socks into the clothes hamper. But we quickly found out that reality hit us very hard in the face with how difficult this should be to make work at scale in every single home. We were probably way too early for the market, and the technology just wasn't there yet. So in 2021, we pivoted to nighttime healthcare robots. These kind of robots look like a wedding cake, and they go up and down the corridors at nighttime, and they stop in front of the residents' rooms. And with a radar sensor, we're able to scan through the closed door to see if someone is out of bed for too long, or in the bathroom, or if they fell over, for example. And then we tell the nurses about this. Generally, we've had a lot of ups and downs as a startup. It's startup life, but it's been a massive learning experience to deploy these robots. And we currently have 4 robots deployed in many parts of Berlin. But anyway, in my spare time, all this madness and technology brought me right here, right now, to this point, the Johnny boy here, picking up the socks. I truly believe we're in the golden age of robotics, the best time to be in this field, and we need more people to explore it. Because everything is extremely hard still. Robotics isn't all sunshine and rainbows. There's so many deep problems and questions within the field, especially humanoids, if we want them to live and work with us 24/7. But I like a challenge, it's a lot of fun, and it's making me a better roboticist. So I've been uploading my streams and creating clips here and there of Johnny's and my journey and other fun things. I'm up to 11 videos in this playlist now, and I'm learning about videography and editing, etc. as I go. This talk itself will touch on many of the same topics as the videos. So I received Johnny back in November, and I can't believe I did an actual unboxing video. And then later I was reprogramming him for sock picking, clutter clearing, and things got quite complicated quite fast. And there's a lot of complexity. Just humanoids are hard. We've had humanoids for about 6 decades, but to get them to do useful things safely is only beginning to happen recently. But overall, I'm working it all out as I go along. I'm having fun. So if you want more details, check it out. Comment, like, and subscribe, all that stuff. The QR code on the top left is for the channel, and the channel URL is there as well. Anyway, back to Johnny. So I bought him from a Chinese company called iWonder. Usually these little humanoids used for robot football, which are programmable, can sometimes cost 10,000 euro or more. but the prices of humanoids in general are dropping. So he has 24 little servo motors. These are the degrees of freedom that he can control. So there's two in the head, one for pan, one for tilt, looking up and down, looking left to right. There's 5 in the arms, so 2 in the shoulder, 2 in the elbow, and 1 in the gripper. The gripper is very important because it allows opening and closing, which allows manipulation to happen. And there's 6 joints in the legs, 3 in the hip, 1 in the knee, that's for kicking and squatting, and 2 in the ankle for ankle pitch and ankle roll. These motors don't have torque control, so we can't see how much force and torque is exerted by the motors, hence why this robot is so cheap relative to others, just position control. As for the brain, it's a Raspberry Pi 5, an expansion board, and a voltmeter display to see how much battery is left. But I often even just use my laptop over the network for running deep learning models. Other extras he comes with is an inertial measurement unit. Every single phone has an IMU to detect angular rotation and acceleration. So it's useful for robots as well. He has a 2-hour battery life, which is pretty good. And he has this kind of okay rolling shutter, kind of bad camera that I have to keep resetting and replugging. I've even thought about strapping a RealSense depth camera on his head, but then he might be more wobbly and walking might not work as well. So let's talk software. So out of the box, the best part, pretty much all of it is provided and can be modifiable in ROS1 Noetic, which means Robot Operating System. It's a typical framework for controlling robots. However, the gait control and leg inverse kinematics for walking are proprietary in binaries, but it just works. So I don't have to worry too much about it. Locomotion that is walking is really hard for bipedal 2-leg robots. And I have bigger fish to fry. I can focusing on abstracting Johnny's walking to a more higher level control problem. How much to rotate his body's yaw angle, how fast to walk forward or backwards. Similar to a differential drive Roomba type robot, except that it has 2 legs. And here you can see him playing football with a visual servoing method, which means very roughly, if the ball is to the left, rotate left. And if the ball is to the right, rotate right. If the ball is close enough, kick. It's a pretty simple method. And he comes with other applications like line following, tracking faces, standing up if he has fallen over. Overall, I would argue that software is the bottleneck in making these robots work. The bottleneck for humanoids not being in all our homes yet. This is proved by the ability of teleoperation when a human controls the robot to do most relevant things that we want these humans to do. And as the great Andrei Karpathy says, if humans can do it, at some point machines can also do it. In some sense, it's the hardest part, software. So that's why I generally focus on this once I have a hardware platform like Johnny. You might be asking by now, why socks? Well, I just find it funny. It gives me a chuckle, the absurdity of life and robots. But also it's semi-useful. It's a semi-useful loco manipulation challenge. There's a reason we haven't seen robots manipulating much in homes, and the reason is it's hard. And I'll get to why. It's also a stepping stone. So the vast majority of useful things humans do is manipulation. A more general version of this sock picking task is the clutter clearing task that has put all the objects into the box. I think this is one of the first use cases for manipulation within home robotics. This is the future I've been waiting for my entire life, and sometimes trying to make happen. But we're finally seeing some companies do it. So on the left here, we see Roborock, their new Roomba-style robot. You can actually buy this for around €1,500. Useful for parents and their kids' toys at the very least. But yeah, my point is the revolution is coming slowly, but bit by bit. And my girlfriend leaves socks everywhere, all over the floor. And at least Johnny now has a purpose to pick them up. So let's solve the problem. You should always simplify, compartmentalize, and even abstract the important parts of the problem. The first thing I needed to prove is, can he grasp deformable soft objects? With a keyframe-based grasp method, which always means the same joint angles for the arm. And as we can see on the left, yes, he can. He can pick up soft objects. Next, since I knew he could play football, we just need to get the sock to the same position and grasp. First, I proved it would work with the red cube you see on the top left, and then with manually drawn rectangles to track with OpenCV across the network on my laptop. I'm surprised that worked. I also improved the visual servoing state estimation of the sock by projecting from the headpan tilt angles towards where that intersects with the ground to find a 2D position on the ground. Said much simpler, I'm just finding a better state estimation of the sock, so Johnny knows where the sock is and he can control himself to get closer. Once that worked, then we just needed the computer vision problem. So once I proved that manually chosen rectangles work, we need to find these bounding boxes autonomously. I mistakenly thought this was going to be quite easy, but even with the Dino V2 foundation model, it's quite hard. Socks are quite a hard object to detect. You can see some false positives in this image over here. And I even tried the vision agent from Andrew NG to detect socks, and you can see even this low confidences on even these socks. So I think I need 3D perception or ensembles of multiple models to improve this accuracy. But it works somewhat well. But this is the real world we're talking about. Moravec's paradox states that the things that we thought would be hard are easy, and the easy things hard. For example, chess or even coding we thought would be harder than truck driving. This makes us think that sock picking is easy. In fact, the simplest things are the hardest for robots. We take our abilities for granted. Everyone listening to this talk is essentially a physical genius, relatively, to robots. And remember, I said that software is the bottleneck. The software of humanoids is difficult and vast. So many sub-problems within perception and control. So many different levels of abstraction and thousands of lines of code and places where things can go wrong. Us robotics or general engineers love to abstract complexity away, but there are limits to this when the real world punches us in the face. So there are many failure cases. I won't go too deep, but not detecting or tracking socks well enough, not grasping well, or not realizing you failed to grasp a sock, standing on the sock that you're trying to pick up, like, holy moly, how the hell are we going to abstract to deal with that sub-problem? How many lines of code to deal with this edge case? Shaky servos, shaky head while walking. He has fallen over so many times. I've been banging my head against the wall, but here is the result. I have to give Johnny a round of applause for 70% accuracy, which is pretty good. And here's an unplanned plan with the same method. You can see the same method. So if you need socks picked up, Johnny's got you covered. Now that sock picking accuracy was somewhat acceptable, I was struggling but making progress for a few months on a more general and useful task, that is, put the socks into the box. I don't have too much time to talk about it, but here's some spoilers and sneak peeks. So on the top right, you see Johnny trying to do a good keyframe action into the box, but he fails because when the arm comes down, it kind of touches the box, and I kind of solved this by retreating a little in the bottom right here. So first try to drop the sock in, and then retreat to get away from the box so you don't fall while that's happening. This is all a bit brittle and hand engineered. This is like classic robotics. I'd love to talk more about 3D perception. It's an amazing field in itself. Um, it's like super cool that we can go from an image to depth estimation with a foundation model for depth, and go to a point cloud from that and do plane segmentation to find the wall, and then use that to find the angle of the wall to help approach the box better. And another kind of tool within the robotics toolkit is behavior trees and dealing with a growing architecture. This is a way to deal with the complexity. But if you're interested, you can always check the YouTube channel for more details. Other cool things I'm doing. So on the top, like there's too much to explore in humanoids. There's only one lifetime, but it's a lot of fun. So on the top right, you can see I explored kinematics and the pi bullet simulation for this mic drop application with the G1 humanoid simulated. I'd love to have more conversations with Johnny with speech to text and an LLM leading to certain actions like give us a wave, Johnny, and he gives us a wave. I have some prototypes of this. And the whole field within robotics is called SLAM, which is about mapping an environment while knowing where you are inside that environment. And I'd love to add the IMU and you do visual inertial SLAM, which is what drones often do to localize themselves at high speeds. On the bottom left here, you see motion retargeting from a human, me, or a person doing jumping jacks to the joint angles of the robot. So you can copy jumping jacks or go from the arm positions. This would enable me to teleoperate him to do more things and then use that data later for imitation learning. And on the bottom right, you see a kind of a basic attempt I was doing at reinforcement learning, just from just tabula rasa, from an empty model. The robot has to learn how to stand just when it opens its eyes for the first time. And reinforcement learning is one way to do this, to make the robot learn to walk and stand up in simulation. But if there's any questions at this point, I'm happy to take them. Cletus, let me know. Otherwise,
Yeah, so in the chat itself, I haven't seen any questions, but I have a couple of my own.
sure.
So you mentioned that software seems to be the bottleneck at the moment. And I'm wondering, my background is more from the hardware side of things, and I was wondering, is the Pi enough to to do all the powering? Yeah.
It can do most of the control software and some very easy computer vision, but pretty much I'm transferring for the big deep learning models. I'm transferring over the network to my laptop to do computer vision, like the foundation model, for example.
Right. So in the future, do you have plans to get everything running, at the edge on the device itself? And what if that is the case? Do you have any ideas what type of platform you'll be aiming at?
That's a great point. I have a lot of experience with Jetson Nanos and Jetson Xaviers.
Yeah.
So Jetson Xaviers have with the Tensor RT framework, they can get a lot of neural networks running, but still maybe not big enough for like a true foundation model. A lot of things will have to, I think, eventually just be running in the cloud, like big foundation models and these LLMs, of course. But certain small models, I think, can run on the Jetson Xavier, Jetson Nano, the NVIDIA platforms.
Right.
Or I'm running a cable or the network on my local laptop, as I'm currently doing.
How is the power consumption when it comes to that? Is it something that you can comfortably run, with how is it even powered, these humanoids?
Oh, so Johnny here is just the LiPo battery.
Right.
I'll go back to the hardware slide. So this 2-hour LiPo 11.11 volt battery with 3.5 amp hours gives it about 2 hours battery. Even when I'm running extra software, it still runs. But again, I'm not running heavy deep learning. It might go down to 1 hour if I'm running it on the Raspberry Pi itself.
Right. Awesome. There are two more questions on the platform, so I'm going to ask them. And then I still have a couple of questions.
Go ahead.
Yeah, so from Moyua, I think the question here is, what programming languages are best to use for this?
In very short answer is mostly Python. Python is my like favorite. It's the best for machine learning, and even for ROS is great for prototyping. And if anything needs to be run faster, you can just do a ROS node, which is the robot operating system I was talking about here. That can be C++ or Python. So certain nodes can be Python, certain nodes can be C++ if you need the speed. But most of the time, the bottleneck, even when you're running heavy Python, it's underneath using NumPy, which is underneath using C++ anyway.
Mhm. Yeah, great. Moyo, I hope that answered your question. There's another question from Danila. And Danila would like to know, with SLAM, did you ever have any difficulties with the walking motion not being so deterministic, and thus having the self states not being so precise?
Oh, I'm trying to understand the question, and in how I understand it, is that maybe the robot is quite shaky, which makes Slam much more difficult. And because the robot is like walking very shakily, the camera is shaking. And yes, that's a really difficult problem, especially with my rolling shutter camera. So this is like at the edge of robotic abilities. There are some new foundation models for Slam that are able to do it better.
Derek, can you please check? I think there's some noise coming in. Please,
Yeah.
could you keep your mics muted while we go through the presentation? As I mentioned earlier, there will be a special session, a Q&A session at the end. So kindly keep your microphones muted so we can be able to keep up with time. Thank you. Yeah, Ben.
I would add to my answer, yeah, pretty much it's very, very difficult for the shaky camera for SLAM to work, especially with a bad camera, a rolling shutter rather than global shutter camera. The more IMUs you have, or the better you do in inertial SLAM with an IMU, the better your SLAM will be. But essentially, it's a very difficult problem. I only have early prototypes at using SLAM for humanoids.
Right. Yes, I think Daniela is quite agreeable with your answer. Thank you very much. I was wondering, what besides you mentioned the IMU, and I think at the point you considered integrating a depth camera. And so on. So my first question would be, what kind of sensors what are you using altogether? And when do you do some sort of sensor fusion in there somewhere? And then also, what would you use the depth camera for some sort of stereopsis, or do you have other plans in mind?
So I haven't used a real like a depth camera with Johnny, but I'd love to. Because getting depth information is super important for robotics. Without it, you're pretty much just using the RGB pixels, and all you have is color information, and you need pretty much very heavy neural networks to be able to do anything with RGB alone.
Yeah.
So with RGBD, which is red, green, blue depth, you can actually build point clouds. What I was describing here for this depth estimation. So even without a real sense camera, you can do depth estimation, which is a pure estimation of the depth with a foundation model that's avoiding a real sense camera. And then you can go from that to a point cloud and do a lot of amazing robotic applications. So often robotics is doing kind of 3D perception rather than 2D perception. To answer your question, real sense is the most common robotics depth camera. And it's great, but it's really hard for me to attach it on the Johnny. As for his sensors, just an IMU and that rolling shutter camera, and of course the encoders for each of the servos, so we know where the servos are. So it's a pretty limited setup.
Yeah, I guess that makes sense, right? I mean, it limits also the power requirements and so on. And I mean, with more sensors, you're going to have to burn a lot more power, need more space to store in the tiny humanoid and so on.
Yeah, And you have to do more software to deal with the fact that you have less data, less depth of point cloud information. So for example, I was mentioning here to make the visual servoing better, I had
Yeah.
to project from the head angle, both the left, right, and the up, down angle
Mm,
towards the ground because I know where the feet are. And using that,
right.
I can actually find out a 3D position of the sock rather than just a 2D pixel position. I found a rough 3D estimate of where the sock is in the world because I did not have depth. If I
Wow.
had depth, I would immediately know. But because
Yeah,
I didn't have depth, I had to do this clever innovation that's very like annoying and is brittle, and
absolutely.
because the head is shaky.
Great, great. So I think that I've exhausted all my questions for now, and I don't see any other questions in the chat. Um, so I guess we can continue, and then probably at the end, if we still have some time, we'll address other questions in the Q&A. Thank you.
Sure. So everything I talked about before was like classic robotics, obviously some foundation models, computer vision here and there, but it's mainly subcomponents and architecture, and you're building all these parts on top of like Lego bricks, and there's a lot of software. So now I'm going to talk a little about kind of more modern robotics and the future of robotics. So I showed at the beginning these kind of three fields that I'm very interested in and that are kind of changing everything within robotics. So this is a imitation learning. So on the top right, this is both Aloha. So on the top right is mobile Aloha, and on the bottom right is Aloha Unleashed. There's a lot of these Aloha papers. Um, on the top right, it actually is able to cook shrimp and high five people just from demonstrations, is able to learn this. Here's rinsing a pan. And on the bottom right is actually tying a shoelace, which is an incredibly difficult task for robotics. Even some people thought this was decades away. But it turns out with enough data, we can get there. So let me explain imitation learning. Right now, most of the most impressive works within robotics is using a form of imitation learning. So the human will teleoperate and collect 50 to 200 demonstrations of, for example, tying shoelaces. And then the model, which I'll get to the models, pretty much just try to predict those actions given the current robot positions and images. So again, the input is the image. It might be multiple different cameras, images, usually RGB. Sometimes it's RGBD real sense, but more often is actually just RGB, normal cameras. So the input is images and the joint positions, and the output is just predict the human actions. What the expert who was teleoperating the shoelace tying, we just want to predict what they would do next. And because deep learning and transformers and VAEs and all these models are really good at predicting and given enough data, they're able to predict well enough what the next action should be. So this is quite similar to what happened with LLMs. Predict the human's next token, given the entire internet. If you see enough data, you're able to predict pretty well what the next token is. The problem with robotics is there's much less public data of these joint angles and images. But that's slowly changing. Some data sets are getting bigger. There's some crowdsourced data sets. And even simulation is another way to scale this data collection. And again, just this flow is collect 50 to 200 demonstrations for one task. And suddenly we're able to do these tasks that we thought were decades away. Just the transformer model keeps predicting the next actions, and when the robot performs those actions, which might just be if there's 7 degrees of freedom in an arm, it might be just 7 numbers representing where those joints should go, which angle for each of the joints in the arm. So that's imitation learning on a high level. More specifically in a framework, there's this new framework from 2024 called Le Robot from Hugging Face, very popular company doing open source machine learning. And now they have this project called Le Robot. And it just enables you to teleoperate arms and then train models to do exactly the thing I'm talking about, imitation learning and some reinforcement learning. And the most impressive thing is that usually arms used to cost tens of thousands of dollars to do these precise tasks with classic robotics. These arms you're seeing here for t-shirt folding sometimes cost $100, $300, and that's just such a like an unlock. It's a wake-up moment for robotics that maybe you don't need expensive hardware with these powerful models that learn from data. So I have two of these SO101 arms, and I'll show you in a bit what I was doing with them. And on the bottom left, you see a t-shirt folding, and on the top right, you see Remy Cadine, who left Tesla to join Le Robot and form this open source democratization of robotics, not just open source software, but also open source hardware. And just it's amazing, like with $300, as the tweet says here, and 100 examples with an iPhone, you're able to fold a t-shirt. And I think a lot of people would be desperate for a general and good enough solution of something like this if it cost $600 or less than $500. Let's see how things change over the next few years. So some very common models for this to deal with this multi-modality. This is a different meaning of multi-modality. There's many ways to fold a t-shirt. There's many ways to go from different angles. So models need to learn how to deal with so many different t-shirt combinations, and t-shirts can be in infinite different configurations. So the models have to learn to deal with this kind of space, this distribution. And another model, so this is ACT from the Aloha papers. It uses the VAE as well. And then another very popular model is the diffusion transformers. So then let's put it in practice. So there was a Le Robot hackathon 2 weeks ago. Like thousands of people took part in this 2-day worldwide hackathon, and I co-organized the local version in Berlin. And below is my part 7 video of the Johnny series, where I'm controlling these two SO101 arms to, guess what? Pick up socks again. The first task was to pick up socks, and the second task you're seeing here was to put the socks into a box. And pretty much with 50 to 100 demonstrations, the model was able to learn to find these socks that can be in infinite configurations with some flaws. Maybe I need better data and a less shaky camera. Here you can see me teleoperating the leader arm to control the follower arm. There's 2 different arms. And then when you're evaluating, this is my meme about socks. I keep calling them deformable soft objects, which is a fancy word for socks. So the model, then we evaluate the model with just one arm. So we use 2 arms. One arm controls the other arm for training and collecting the data. And then we evaluate just on one arm moving. And you can see kind of this other arm, this leader arm, has a handle, which makes it easy to control this second arm. The leader arm controls the follower arm. So this is an awesome hackathon, and things are really changing now that thousands of people worldwide are doing all sorts of things. One of the submissions was someone playing air hockey with these arms. So it learned how to play air hockey and many other different cool applications. It's kind of things are changing in robotics, and all thanks to Le Robot. So that's imitation learning. What comes next? It's foundation models. So pretty much everything I showed before with imitation learning was one task. We collect demonstrations for one task and then try to train on that task and evaluate on that task. Foundation models, VLAs, vision, language, action model, which not just do vision, language, they combine all 3, are able to do multiple tasks because they take in general text input like an LLM, and then they output actions. So ACT was a single task model, single diffusion policy was a single task model, and then along comes Pi0 from the Physical Intelligence Company, and it takes in general text and is able to do multiple or hundreds of different tasks to some accuracy. And since then, there's now a race to create these VLAs, VLMs. So NVIDIA has the Groot 1.5 model, Figure has the Helix model, Gemini Robotics even released another model 2 days ago. And they're often actually combining 2 different levels of these kind of models. So one is a very slow LLM, a very large LLM that can even live on the cloud, that has maybe 8 billion parameters or even 50 billion parameters, and it's running at like 10 hertz, 10 times a second, or even slower. And then there's this fast model. This is like the ACT model, which is even 100 million parameters only. And that's just directly outputting actions at a very high frequency, which is needed for robotics. And this is like from Daniel Kahneman's book, Thinking Fast and Slow, System 1 and System 2, Fast and Slow Thinking. These were inspired by psychology to make these robots do things. And on the bottom left, you see kind of Helix showing these new scaling laws. As the robot gets more and more data, it gets faster to learn new tasks, and you need less and less data. In the beginning, traditional approach, this classic robotics, you needed PhDs one PhD would do one task for 4 years. Things are kind of changing now with a fleet model and more robots and more data. You can scale faster to more tasks. On the top right is this physical intelligence I was talking about. It's folding a box is one task here, and then you can see the hundreds of other tasks it is doing. So that's foundation models. And then, but this is still just imitating humans. How do we get to superhuman? The only way to do this is right now is pretty much with reinforcement learning. The same is happening with like language and LLMs, with reasoning models. They're becoming better than their initial data by being able to build their own data and learn from their mistakes. That's the reasoning models you hear about with Gemini, etc. They're able to then maximize reward with RL to then get better and better reward, especially if you can evaluate how well the model is doing. So RL began to be used for walking. So a lot of models were using it for walking, but now, as you see, it's moved on to stunts. So even Boston Dynamics is doing cartwheels. It's breakdancing better than me. On the left here is a foundation model from Meta. And you can see it's trying to copy this cartwheel. And after 100% of training, it's able to do the cartwheel. So Boston Dynamics did a similar method to learn how to make their electric Atlas model to do a cartwheel as well. And it's not just for whole body locomotion and control. It's even for crazy manipulation tasks that are really hard to specify and even control. So one is this Jenga whipping. On the top left here is HIL Searle, so human in the loop. And it's able to get 100% accuracy on 13 different tasks. Not so with imitation learning, you might only get 70% accuracy, 80%. But with RL on top, we're able to even get to 100% accuracy. So I'm really excited for the follow-on papers to this. So it's just whipping out a Jenga from the top without knocking the whole tower over. It's quite, I don't know if I could do that. Cool. So that's reinforcement learning. And it's how we get to superhuman from a base imitation learning model, and you can make these foundation models even do more than what they're just imitating. Similar is happening to LLMs, as I said. Anyway, another kind of problem with ORL, though, is data and running in the real world. So simulation is one way to solve this, but the issue is the difference between the real world and the simulation. So that's why the field of sim to real has existed for a long time now. How to learn from the simulation and apply it to the real world. So here we see a robot that was actually trained in simulation and is able to then be on top of a ball and use the ball to walk around city streets. But even on top of that, it's not just that they transferred from the simulation to the real world, it's that an LLM, a language model, guided the whole process of sim to real. It built its own reward functions and domain randomization to then build a good enough sim to real pipeline so that when the real robot saw this, it was just another world in its many different simulations that it's seen. It's just another world out of many different random simulations. And because of that, it was robust enough to be able to walk on top of a ball and use that to walk around. So again, to reiterate, the LLM guided the whole sim to real process, designed and coded the reward functions to make this sim to real work. And that's so impressive. Maybe there's a path to being able to do much more with robotics. But progress is both fast and slow. It kind of these things happen over many years, and then you get papers like this. There's been many previous results getting us to here. So, to recap, what is the future of Johnny and robotics as a whole? There are three areas I talked about, which are making rapid progress. Imitation learning is actually working extremely well for difficult tasks, once thought decades away. This leads to foundation models, which take general text input and able to complete hundreds of tasks to some accuracy. It might be 70%, 60%, 80% accuracy. It's really hard to get to 100% accuracy. And then reinforcement learning is a way to scale this even further. Boston Dynamics on the right, again, doing breakdancing. I could talk about the future of humanoids for hours, but in short, a lot of what I talked about with Johnny is classic robotics, explicitly estimate the state of the world, plan, control, react, a lot of hand engineering. Classic robotics likely won't scale to thousands of tasks. The future of robotics is more implicit. Let general action models learn what is important and correct. The same happened to computer vision in 2012 and NLP over the last decade. That's why I'm pivoting more towards these three areas. So deep learning is underlying all of this. It's able to learn the patterns in the data. So that's why I think this software in particular is the holy grail of robotics, if it works. However, real-world deployments of tens of thousands of humanoids might take longer than the hype indicates, but progress is happening fast. For 7 years, I was impressed but doubtful it could actually scale, but now I'm much less skeptical. I'll go to the Coral, the Robot Learning Conference in Seoul, South Korea, to check this robot learning bubble out. And to conclude, this is why I think we're in the golden age of robotics. There is a path to dealing with the real world's complexity. Anyway, I'd like to thank Claude 3.7 and 3.5. Of course, DeepSeek, O3, not so much. Of course, Johnny, my girlfriend, for dealing with my absurdity and her socks. And my thoughts go out to all the GIFs that didn't make the cut. Please subscribe to the channel. On the top right, you see this QR code. It motivates me, so it takes a lot of work to make these videos. And my LinkedIn is on the bottom left. And thanks for having me.
Wow, amazing presentation. Wow, thank you so much. I'm so yeah, I'm blown away, especially with a dog on the yeah, on the ball. Like, how did they do that? Wow, amazing. So I think what we're gonna do now is open the floor. So if anyone has questions now, you could literally unmute yourself and ask them directly. You don't even need to put it in the chat. So it's literally question and answering time. Derek, could you please make it possible so that everyone can unmute themselves when they want to, if they want to. Thanks. Yeah. So if there are any questions at all, I think we have about 10 more minutes. Timing was perfect. Enough time to address any questions in general.
I'll just show a few slides in case it triggers any questions.
Yeah. So I think maybe we'll just wait for about 30 seconds. If there's no question, maybe you can, continue to show more stuff. I've never heard of vision language action models before.
Mm-hmm.
I mean, you went in there a bit, to describe them also as foundational models and so. Now, how I understand foundation models when it comes to large language models, is there a correlation there?
That's a good question. I think generally what is meant by foundation models is just training on enough large data for a specific subset of data. For example, there's a foundation model for depth estimation. There's a foundation model for finding the pose from a camera. There's a foundation model for even action. It's a bit of a loaded term. It can kind of mean whatever you want as long as it's a very big model and a lot of data. So vision language action models. Like I would say most LLMs are foundation models of text. Uh,
Right, exactly.
and then what happened recently over the last year or more was we started adding language and vision. So now you can ask any ChatGPT Gemini model, you can send a picture and say, what's in this picture?
Yeah,
Or translate, or like you can take a picture of a page from a book and say, transcribe this entire page. So they've become very general models for vision and language. And then it's a pretty easy extension to just add action on top instead of just outputting text, which is what usually LLMs do.
yes,
They get given input of
and predict
images
the
and
next step.
text, and out comes more text, sometimes images.
Yeah.
But now it's another easy addition to just output actions, even at 100 hertz or 5 hertz, and that's how you're able to control actual robots with these models.
Oh, amazing. Yeah. Are there any questions in the chat? Let me check once again. Um, right. So Alex says, that is amazing what is happening in this field, but I'm curious if classic robotic algorithms die out because of the new approaches like reinforcement learning, or would be used in some cases.
I'm not. I wonder if the question is like, if it dies out, what do we do then? Is it like is it a sad thing, or is it, what are we going to do with the old methods? Um, I'm not fully understanding the question, but I can
I,
answer
I,
it.
I think if I understood him correctly, it boils down to the same question everyone is asking today: AI replacing your job and so on. So with things being done, in a more specific way, we're using more classic robotic
Yeah,
algorithms,
I
and
mean,
obviously,
so the same happened. It's like AI is eating the world, deep learning is eating the world, eating software. So the same happened with computer vision. People would build all these hand-engineered feature pipelines to detect cats or chairs, but all like they were using SVMs and handcrafted features. But in 2012, all of that changed with AlexNet and ImageNet. And now we don't do those approaches for computer vision anymore. You can still do it for maybe some very small cases. And then similar happened with language. And kind of what I'm arguing and what I worry for also is that the same is going to happen with robotics. But maybe until it happens, there's always going to be some hybrid approaches. So as I showed with Johnny, Johnny was using foundation models for some parts of his like for some sub problems for detecting the socks, but not for doing everything. That's like end-to-end learning. I've been debating this in my own mind for the last 7 years. Is like, really, do we want to replace everything with end-to-end learning? And kind of the same question is a very deep question, and the field hasn't decided. And for example, self-driving is a what happened over the last 10 years with self-driving is now the two main winners either take end-to-end learning approach like Tesla and Wave versus Waymo, which takes a more classic robotic learning approach with lots of deep learning networks within to solve sub problems. And it's like whether to just make the neural network learn everything from data, or should you actually design some hybrid algorithms that use deep learning with combined like with classic robotics. And this is a debate that hasn't resolved yet. And it's like Waymo has millions of hours now in self-driving, but so does Tesla. And I ask myself the same question pretty much every day, but I am pivoting more into deep learning that will output actions as is kind of like an end-to-end learning approach. With much less software, you're just collecting the data instead and doing more machine learning and data science rather than robotics engineering.
yeah, that's true.
Yeah.
Yeah, especially
Like,
from the driverless vehicle space.
yeah.
Yeah, obviously that's my field. That's where I come from, so I can totally attest to that.
Yeah. And I mean, so there's lots of complexity with robotics classic software, But there's also lots of complexity with data collection, recording hundreds of or thousands of demonstrations. Actually, it's not all like sunshine and rainbows. What you're seeing with this shoelace project on the right, on the bottom right here, that took 8,000 demonstrations from Google. So that's literally hundreds of hours of work from uh, teleoperators who are controlling these two arms. So that's so much data. And will it work with every shoe? I don't know. How much generalization comes out of these models? So the battle still rages on in the field of how much end-to-end learning can win versus how much you should do hybrid learning. And I still debate that every day.
Yeah, that's yeah. I think Alex is quite satisfied with your answer as well. He says thank you. Yeah. So are there any more questions? Are there any more questions at this point? We have just 3 more minutes to go. So are there any more questions? Okay. So someone is asking, what's a beginner-friendly project to start with robotics with Raspberry Pi, or even without a physical hardware first, mostly about implementation with software? That's a good question.
Yeah, really good question. So without hardware, because hardware costs money, I'm always trying to optimize. I can't afford a 10 grand, 10,000 euro arm. One solution to that is simulation. What I showed you here was actually trained in simulation and then transferred to the real world. You can actually do the whole pipeline in simulation. And then if you have the robot, you can transfer. The other example that I showed in simulation was this mic drop application. All of that is without hardware. You just need a
Mm.
pretty simple CPU. You don't even need a NVIDIA GPU to run this simulation. So there's a
Mhm.
lot of basics software you can do with just pure Python and PyBullet and ROS and simulation. As for a Raspberry Pi, there's lots of projects you can do with that. It depends if you want to learn electronics first, like to turn on LEDs or control motors. You might want to use Arduino. Depends how low level you want to go. I personally prefer, as I said, since software is the bottleneck, I personally prefer to just buy a platform like Johnny, and he just works out of the box. You can buy cheaper robots for 100 euro, 200 euro. These arms I was showing you, they're just 100 euro, 200 euro, or pounds. And then you can use them. They're pretty cheap, pretty affordable. Um, and you can, but if you want to actually specifically get a Raspberry Pi, then I recommend learning ROS and some basic ROS for that, and then simulation, as I said.
Ben, I think if you have some books, some channels, some links that could be of help, you can post them later in the chat, or you can send them to me, and then I'll forward it to whoever needs it. Thank you
Yeah.
so much. I think there's another question from Nicole. So Nicole says, amazing work, Ben. How have you balanced the trade-offs between mechanical complexity and software intelligence whilst designing?
Hmm.
Mhm.
I don't fully understand, but I'll answer it in the way I do understand. So like there's obviously so much complexity in the hardware itself. Luckily, I didn't have to build the robot myself. Sometimes I have to unscrew things or replug wires. Uh, but even in the like complexity of the hardware, as you see on the top right, the robot still falls over, which is I would say is mostly a software problem. I didn't fully understand the state of the world. Um, Also, as we had the big conversation about sensors, I don't have enough sensors to understand the full state of the world, to understand the box was underneath the arm. So you need to program that in. So you just need more and more software, and it's really complicated. And part of why I'm pivoting towards these vision language action models is to get away from this complexity of the hardware, but also the complexity of the classic robotics. As one way to do that is you just do these end-to-end learning models with enough data. It becomes a machine learning problem, a data science, data collection problem, and you're just kind of optimizing models. And these cheap arms, even though they're shaky, even though they're not the strong, most precise motors, the model, the intelligence is able to deal with the complexity of folding a t-shirt, no matter how shaky the arms are. So that's one way I try to get away from that. I'm trying to remove some complexity on the software side and the hardware side by changing the software to these end-to-end learning models.
Awesome. Awesome. Yeah, thank you so much. So I think we are on the top of the hour. It's 8:31. Just 1 minute past. Yeah, so we did quite well with the time. Thank you so much, Ben, for the amazing presentation. We've learned so much, and for the amazing work that you're doing. Yeah, it's very impressive. So thank you so much. And I think we'll be coming to you. If anyone has questions, you can please, again, follow us on our Instagram channel, the YouTube as well. You can send the question in the meetup, in Instagram, Ride.ai, both channels. And we can direct this question to Ben, or you can ask directly. I think he gave details to his channels as well. So once again, we come to the end of another successful webinar. Thank you so much for tuning in. Thank you very much for your audience. And yeah, we hope to bring you another session in AI. Thank you so much and have a wonderful evening.
Thank you.
Bye.
Thanks for having me.
Yeah.